today we're going to start talking about Chapter 3, which is graph theory. And to motivate this, we start with a couple of warm-up problems. So you should have already started these problems on your own. If you haven't tried the warm-up problems, go and try them now. Oh, wait. No, I'm just kidding. I won't wait. Pause it, go try them, and then come back. Okay, so in this first problem, we have that a band is planning a tour of 9 states in the Northeast, and they want to pick songs so that any 2 states that are adjacent to each other, that share a border, don't have the same encore song at the end. And so hopefully you've tried this out yourself. I've drawn a solution here where it's possible that the band only needs to prepare 3 songs here, right? They could play this first song, which I've highlighted in pink and I've labeled 1 in Maine and Massachusetts, in New Jersey. They can play a second song in Rhode Island, New Hampshire, and New York, and they can play a third song in Pennsylvania, Connecticut, and Vermont. Now, your way of grouping these songs might have been different from mine, but just keep in mind that any 2 states that are touching each other need to have a different song, a different color, a different number, however you wanted to label it. Now, is this ideal? Is this the best possible number we can get? That's a good question to have. So is it possible that they could play a fewer number of songs? This isn't actually the least, that there could be a fewer number of songs. Well, if you think about it for just a second, it should become clear that you need at least 3 songs. Because, for example, we have 3 states, Vermont, New Hampshire, and Massachusetts, that are all touching each other. Right? These 3 states are all touching each other, which means all 3 of them are going to need their own song. So we know that we need at least 3. Right? We need at least 3. Since New Hampshire, Vermont, and Mass are all touching each other. And we know that it's possible to do it in 3 because I did it right here, which means 3 is the magic number here. 3 is the number of songs that they're going to have to prepare. Okay, now this was easy enough to sort of play around with and guess and check, but it's probably a lot harder if you think about a much more complicated map or a much bigger map. If we wanted to do this for the entire United States, for instance, yikes, that would be sort of a mess. All right, so problem 2 is kind of a similar style in some way. We have the math department is planning to offer 10 classes next semester. Some classes cannot run at the same time. How many different time slots are needed to teach these classes? And in particular, okay, obviously you could do it in 10 different time slots, just give every class their own time slot, but we're trying to find the minimum number needed. And once again, this is a type of problem that we could do with guess and check if we needed to, right? We could just sort of start playing around with things and say, all right, here's my first time slot. Maybe I'll put class A in there. But once I put class A in there, I know that D and I can't be in that first time slot because they conflict according to the table. So we need a new time slot, call it time slot 2. And can I put D and I in there? Well, D doesn't conflict with I doesn't conflict with D, so yes, let's put D and I in the second time slot. All right, and then we keep going down the line. Class B doesn't conflict with A, so I can put it here in the first time slot as well. Class C doesn't conflict with A or B, so I can put it in the first time slot as well. Class D, okay, D conflict, oh, we already have D, sorry. E doesn't conflict with A or B or C, so we'll put E in that first time slot as well. F conflicts only with I, so F can go in the first time slot as well. G conflicts only with J, so we can put that in the first time slot. H conflicts with E, I, and J. Uh-oh. So it conflicts with E, which means I can't put it in the first time slot, and it conflicts with I, which means I can't put it in the second time slot. So I guess I'm going to need a third time slot here for H. Okay. I is already somewhere, and J conflicts with B, G, and H. Well, B and G are in the first time slot, and H is in the third, but there's no conflicts here in the second time slot, so I'll put J here. All right. Now, again, guess and check was enough here. We were able to split it up into 3 time slots, but how do we know that that's minimum? How do we know that it's impossible to do it in any fewer? Well, we want to use the same kind of argument we made up here. We want to find 3 classes that are all sort of mutually conflicting with each other. And we sort of did that already when we justified why H needed its own time slot. H can't be in a time slot with E or I. E can't be in a time slot with H or I. And I can't be in a time slot with E or H. So E, H, and I all need their own time slot. So 3, or at least 3, time slots are needed. This is giving us sort of a lower bound here. It's saying we need at least 3 time slots, but we also have kind of an upper bound because we've shown that it's possible to do it in exactly 3. So 3 is sort of our magic number here as well. Now, just like before, you can imagine that this would get a lot more complicated and a lot more difficult to do using guess and check if we had, say, 100 classes. The math department offers over 100 classes. So this would be a much harder problem to do by guess and check. And so graph theory gives us a way of handling this type of problems, of sort of generalizing it to a particular kind of math that can handle issues like this. So let's go over a short introduction to graph theory and then see how we can use it to address these types of problems. Okay, so zoom out a little here. All right, this is an introduction to graph theory, and then we'll get to graph coloring. So what is a graph? You've probably been exposed to graphs a lot in maybe algebra or calculus, but that's not really the type of graph that we're talking about when we talk about graph theory. So for us, a graph is just an ordered pair consisting of a vertex set V and an edge set E. So these are each sets here, V and E. And so the vertex set is just a set of elements, right? Those things could be anything. And then in particular, the edge set needs to consist of 2 element subsets of V. So this seems like a pretty abstract definition. Let's try to think about what it really means. I'm going to give you an example here and say that the graph G is consisting of the vertex set V, which has elements A, B, C, D, and little e in it, and the edge set E, and that edge set needs to consist of 2 element subsets of the vertex set. It doesn't need to be all 2 element subsets, it just needs to be some of them. So for example, we have AB, we have AC, AD, BC, BE, and DE. Now, this is the way that we define a graph, but the way that we think about a graph most often is using a diagram. Okay, and so the vertex set is really just going to be points, right? Dots. So we've got point A, point B, C, D, and E. I drew them in a circle like this, but it really does not matter how you draw them. You can draw them however you like. And then the edge set is telling you a relationship between pairs of vertices. So for example, the fact that AB is an element of the edge set E means A and B are connected in some way. We're trying to express some sort of relationship between A and B. And so in our diagram, we can represent that using some sort of a line segment to connect them. It doesn't have to be a straight line, right? But just some sort of curve that's connecting points A to B, right? Because AB is in our edge set. Similarly, AC is in our edge set, which means A should be connected to C. AD is in our edge set, so A has to connect to D. BC is in our edge set, so B connects to C. B connects to E as well. And then finally, D connects to E. So in the end, we get a diagram that looks like this. Okay? Your diagram could look different if you drew your vertices, right? We call each one of these a vertex set. Plural, they would be vertices. If you drew your vertices in some other order, this graph might look a little bit different. But all you really need for a correct graph here is for all of your vertices to be there. So we have all 5 of our vertices here. And for there to be some sort of a line connecting each pair of vertices that show up in the edge set. Okay, so notice, for example, the set CD doesn't occur in the edge set, so we don't have a line connecting C to D. And similarly for A to E. So we don't need all of the 2 element subsets, we just need some of them, right? Now, the order of G is defined to be the number of vertices. In other words, the order should be the size of the vertex set, the cardinality of the vertex set. In this graph here, our number of vertices is 5. Okay? The size of G is defined to be the number of edges in your graph, the number of lines connecting, right? Connecting lines. So that's going to be the cardinality of the edge set. Well, it's sometimes a little bit harder to count it on the graph itself. You want to make sure you don't double count, but you've got 1, 2, 3, 4, 5, 6. It's easier to count it up here. This is one edge, 2, 3, 4, 5, and 6. So the size of this graph is 6. One more definition. We say that if UV, before I do that, writing out the edges like this using a whole bunch of curly brackets can be pretty tedious. And so oftentimes when we describe the edge set, instead of actually writing out this subset AB in curly brackets, we'll just write AB together. And you could write AB, or you could do it in the other order BA, because there's no order to a set. But this is just saying that there's an edge connecting A to B, and vice versa. Then we have AC, AD, BC, BE, or DE, right? This is just a shorthand way of describing the edge set. Okay, now with that in mind, if UV in general is an edge of a graph G, then we say that U is adjacent to V. So in our example above, we could say something like A is adjacent to B because AB is an edge in our graph. There's a line connecting A to B, but C is not adjacent to D. All right, so maybe already you can see why this sort of an object in math can be useful. It's describing relationships between pairs of elements. And we'll see that we can use this to help us in the warm-up problems in the next video. But for now, I'll give you one example of how we can use graph theory in an application problem. Okay, so this is called a matching problem. So suppose that we have 4 employees and they need to complete 4 tasks. And we know that some of the employees can only complete certain tasks, not all possible tasks. So one question you might want to ask is it possible to assign one employee to each task? So I've drawn a graph to model this situation. So I have 4 employees, A, B, C, and D, and I have 4 tasks that need to be completed, E, F, G, and H. And I drew my graph in such a way that if there's an edge between an employee and a task, that means that employee is capable of doing that task, right? So employee A can complete task E or complete task F, but they don't know how to do tasks G and H, etc. So what would it look like to try to solve this problem using the graph? Okay, well, think about it for a sec. What we're trying to do is find a way to assign one task to one employee in such a way that all 4 employees get used and all 4 tasks get completed. Okay, well, let's try to think through what would need to happen here. Task F can only get completed by employee A. Nobody else knows how to do that task, which means when we do this, we're going to have to assign task F to employee A. All right, now employee A has already done their task. They're not going to be able to do anything else, so they won't be able to complete task E, for example. But that's okay, because employee B also knows how to do task E. So let's assign task E to employee B. All right, other issues here, employee C only knows how to do one single task, and that's task G, so we're gonna have to assign task G to employee C. And finally, we have 1 task and 1 employee left, and luckily, employee D knows how to do task H, so they'll get assigned here. Okay, so this is called a graph matching. We found a way to match up employees to tasks in a way that you can see, based on our highlighted edges here, this is a bijection, right? It's 1-to-1 and it's on 2. Okay, now let's look at a similar problem, but with different employees and different tasks. Is this possible? Is it possible to get a matching here? Can we assign tasks to employees so that every employee does exactly 1 task? I mean, we could try, right? For example, L can only do task M, which means we would have to assign L to M. And K can only complete task O, so we would have to assign K to O. And well, now we have a problem because there's only 2 tasks left, and the only person who knows how to complete both of them are J. Right? The other issue is I only knows how to complete task O, but somebody else is already doing task O, right? So there's no way to actually complete these last 2 tasks using people I and J. So it's going to be not possible here. And this is a whole area of graph theory, the idea of using of graph matching to try and figure out if it's possible to assign vertices in one set to vertices in another set using the edges of the graph. Okay, but I claim that we can also use graph theory to help us address the types of problems that we were doing in the warm-up. Right, so I'm going to give you one more similar problem here. So suppose that a state is divided into counties, as in this map below, and the map maker wishes to color each county. But if any 2 counties share a border, we want to make sure that they don't have the same color. The question is it possible to do this? So I'm going to stop this video here, and we'll come back and try and answer this with graph theory in the next video.